Any questions? Any questions? One of the things that's missing for this class is we are going to have one lab session next week or the following week. I will email you again. The assistants are working to prepare an experiment over there for you. Okay? It will be kind of a demonstration. You can use your feedback gains and all that. It will be kind of a fun thing for you to do. Okay? All right. Any questions on this? You have to, as I said, I could have just written you this. Okay? But I wanted to show you where things are a little bit coming from. And if you are missing some of the pieces, it is okay. I just want you to understand that where this idea is actually coming from. All right? So one thing you might ask, of course, is that S dot is a differential equation. So it must have a starting point. How do you solve this S dot? It's a differential equation. You need a terminal point, right, at the beginning or at the end. Well, you have it over here. This is something we never used. And you could use this, and this d phi, this part here is phi, remember? This part was phi. So if you take the differential, the derivative with respect to x df, you will get s over here. And this will be kind of the terminal constraint to solve this in conjunction with that. So I'm not necessarily giving you everything here, but you understand that this is solvable because you have these terminal constraints for the equation. I mean, instead of this lambda dot equation, now you have another differential equation. It's an S dot equation. Okay? So you could still solve this equation. Now, this is the more general solution with the Riccati equation and with the terminal the terminal function in the optimization problem. Now, you can have this problem a little simplified, okay? And for which I'm not going to solve everything, the solution, but you can imagine that the solution is somewhat similar. But you can make this problem a little bit simpler, and it will help us too, because if you see, this goes to T final. So for our controller, T final is not necessarily a very good scenario. I mean, we don't really have a T final when an airplane flies, right? I mean, imagine an airplane flying for 10 hours. What is T final? The end of the 10 hours? It's not, right? I mean, you might want to think of this as one maneuver. So T final would be the end of a maneuver, right? You give a step input and then you have the end of the maneuver, so that would be T final. So that kind of makes sense. But a more meaningful problem would be if I had this. And this is maybe a special case. Maybe that's what I should write. Where phi is equal to 0, special case. Is when I do this. You might want to put a dt over here. This. I mean, we are so used to writing that integral. Of course, it's an integral in time, right? So what did I do? I said here phi is equal to 0, right? That's one thing, so that the final time term is gone. Okay. Another thing, t final goes to infinity. Okay, you can change the problem to this. And you can still make that assumption. Still assume, and this is still subject to x dot is equal to ax plus bu. And you can still assume a solution to s times x of t. If you do that, if you solve this special case, this is somewhat a special case, follows kind of the same procedures. If you solve this case, you will end up with the following. The solution to this, it's kind of interesting. The s dot is dropped, and you will get 0 is equal to SA plus AT times S minus S B G over minus 1 BT S plus F. And this is, again, it is called the algebraic Riccati equation. And the way you see it, there's no s dot, so it is not a differential equation. It is an algebraic Riccati equation. So it's an algebraic equation that we can solve. And the controller, u, is still will be the same. U is equal to minus g minus 1 bt times x t. Okay? And this is what we call the infinite time solution. This is what we call infinite time LQR problem. Okay. Change the problem a little bit, remove the terminal constraints, so no guarantees on the terminal time. Okay. There could be steady states and all this, no guarantees on the terminal time, so that's gone. That's not part of the optimization problem anymore. Phi is equal to 0. And t final goes to infinity. Okay, we take that to infinity. Still have that assumption. If you solve this problem the way we solved, very similar. This is the more generic form, of course. This is more general, and you see you have to solve a differential equation here, which makes this problem more difficult to solve. Okay? This makes it more difficult to solve, so the optimization is a little more involved here. Simplify the problem a little bit, and you obtain this one. This is called the Riccati equation. The only thing that's removed is s dot. Okay, s dot is gone. So it will be algebraic. This is not a differential equation anymore. But the solution is still the same. G over minus 1 bt s x t. And what you're seeing here, this is a classic LQR solution. Okay? So K will be a constant matrix, where this part here, of course, is K. So K is equal to G over minus 1 BT times S. Okay? Although S is not in the problem anymore, we have a variable called S now. It's not in the problem, it's a variable called S that still appears in the solution. And S is a function of A, B, G, and F. That's over here. It's an algebraic equation. It's not a function of time. In fact, this is valid as time goes to infinity. So it will reduce the movement in x and u and really does not look at the final x. Okay? So this is a somewhat simpler problem. Easier to solve since there's no differential equation for S. It's called the infinite time LQR problem. And if you would ask somebody in the industry to calculate an LQR gain, this is what people would calculate typically. Okay? There's a distinction between infinite time LQR problem and the finite time LQR problem. Okay, I call it the finite time because this goes to T final. It has to have a stationary point at the end. This here is the infinite time problem because it goes to infinity. Okay? And the solution of this one, though it is somewhat more useful in industry because it goes to infinity now, the solution is actually simpler because it doesn't have the differential equation as that in this equation. So this is an algebraic equation. And this is called the algebraic Riccati equation. Okay? So don't forget Riccati equation, algebraic Riccati equation, LQR solution, and where this is coming from. Is that okay? Does it make sense? And this one gives you a k value that is changing with time, right? S is changing. Here k, S is not changing because this is now an algebraic equation. You will get k, a fixed k number. That's fine so far? Any questions? So the application is very simple. In the problem, what do you need to solve this? Well, the problem will give you the linearized equation, x hat equals ax plus bu. We give this all the time, right? So you have a and b. So the only thing that you don't have is now f and g. If you know f and g, then the solution is very simple. You plug this in, you find s from this equation, the algebraic Riccati equation, plug it in here and you have the k value. That's it. So question is now, who is going to give me f and g? Well, that's the job of the designer. You are going to choose f and g. Nobody's going to give you f and g. Okay? You are going to choose f and g. So the problem only needs f and g to solve because a and b comes from your dynamic system. It's still the linearization of the dynamic problem around an equilibrium point and all that. So this is given. What you need to choose is f and g. Question is, how do you choose f and g? Okay? And this is the job of the control engineer, to choose f and g in a meaningful way. Okay? Now, nobody is giving us desired eigenvalues anymore, right? Instead of desired eigenvalues, now we are going to choose f and g. There has to be some freedom for the controls engineer, otherwise it would be a dull problem, right? Someone would give you f and g, someone will give you a and b, all you need to do is solve this. In fact, solving this is very straightforward. In MATLAB, it's one command. Okay? In MATLAB, you just write k equal LQR A, B, G, F. And there's a 0 here, but you'll see. So you'll get A, B, G, F 0, and it will calculate you k immediately. You just need to plug in A, B, and then choose G and F. It will calculate LQR. So that's not the problem. The problem is not solving this. MATLAB does it in less than a second. The problem is, how do you choose G and F? Does that make sense? Okay. So how do you choose it? In order to choose it correctly, you need to understand what G and F actually means for the optimization problem. Okay? So let's go one step back and try to remember what the optimization problem is trying to do. The optimization problem is trying to minimize J. That's all it's trying to do. And J is a number. It's not a vector, it's not a matrix, it's a number, right? You multiply a vector with a matrix and a vector, you get a number, right? And it's called a quadratic regulator because it's like taking the squares of x's and taking the squares of u and multiplying it with a number, all right? So you're trying to minimize j. So let's think of this like that. J is a number, right? And let's say for different x's and for different u's, I can't really plot it right now. Let's say j is a function that looks like this, and it's trying to find that. All right? It's actually trying to find the minimum by changing x's and u's, and x and u is not really independent. It is dependent through this equation, so it's trying to do that. So let's think it like that. If f was a large number and g was a small number, and when I say number, of course, these are matrices, but maybe to simplify the problem, let's think first that x is a scalar, and let's think u is a scalar. In which case, f and g would also be scalar numbers, and this would be scale variables. Okay, so this would look like this. J is equal to 1 over 2, 0 to infinity. It would simply be f times x squared plus g times u squared times dt. Okay, let's think of this first as one-dimensional variables and these ones as scalars. So if I want to minimize j, then x and u has to become small, of course. But they are multiplied with numbers f and g. Now here's the question. If f was a large number, let's think of f as a large number, and g is a small number. And when I say small and large, let's make it 0.1 and f make it 1000. Okay? And let's say x and u are comparable numbers. Okay, they are all degrees, let's say. So if f is a very large number, a small change in x, okay, would have a big effect in j, right? And the same amount of change in u, because it's multiplied with 0.1, it would have a small effect on j. So if I want to minimize j, the problem will try to minimize x as much as possible compared to u. Because u can be 10, then it will be multiplied with 0.1, then it will be equal to 1, this part. But if x is 10, it will be multiplied with 1000, so it will be 10,000 over here. So meaningful would be to minimize x to 0.1, and u can be 100, doesn't matter. And it would still minimize j. Does it make sense? No. Let me do it again. Can I remove this part? I guess I can. Let's give an example here. Let's say f is 1000. Okay? And g is 0.1. Okay? And say j is equal to f plus 0.1 g dt. Say again? Okay. Can you read it? All right. So let's say you want to minimize that. And compare that to another problem where f is equal to 0.1 and g is equal to 1000. Okay? So this is case 1, example case 1, and this is example case 2. And the goal is to minimize j. So, okay. this is what I'm claiming. In this problem, the optimization problem will try to minimize x a lot more than u. Because if x is small, then it will be multiplied with a large number. If u is small, it doesn't really matter, it's still multiplied with a very small number. So if u is large, it doesn't matter too much because it's multiplied with a small number. So in terms of the optimization, u is not very significant if you want to minimize j. It's more significant what you do with x. Understand that? If you want to minimize j, it's more important what you do with x. So the minimization problem will try to minimize x a lot more than u. Because if x is, let's say, x is equal to 100, it will be a very large number. If u is equal to 100, it will not be a very large number. So the optimization problem will try to do this probably. X is equal to 0.1 and u is equal to 10. And it will still minimize this j. Because x will become smaller, but it's multiplied with a large number. And u is equal to 10. It doesn't really matter. It's still multiplied with 0.1. So this is a better solution than this. Okay? Or maybe to compare, let's do it this way. Maybe this is a good way to explain this. Which one is a better solution? X is equal to 0.1, u is equal to 10, or x is equal to 10 and u is equal to 0.1. Which one would be a more preferable solution for this? The first one, obviously, right? Why is the first one? Because it's multiplied with 1,000. So if you want, and u and x are connected, of course, right? I'm just making these numbers up now. But you would try to make x smaller compared to u if you set up the problem like this. Now for the same problem, let's change f and g. Let's make 1,000 over here and 0. Which one would be a better solution for this one? The second one would be better because u would be small, you multiply it with a large number. So if you try to minimize j, if you set up the problem like this, you will get a solution where x's are small and u's are big. And if you set it up like this, x's will be large and u's will be small for this one. Do you understand? Do you understand it? So since you are choosing f and g, if you choose a large f, it would mean that x will not move too much. The optimization problem will try to minimize x, but allow u to move a lot over here. Understood? If you choose it the opposite way, if you choose a small u and a small f and a large g, then that would mean that u can move a lot and x can move little. No, opposite. X can move a lot and u should move little. So it will choose a solution because the minimization problem is choosing u's and x's. It chooses a combination of u's and x's to minimize j. That's the optimization problem. Right? The optimization problem will choose u's and x's to minimize j. That's what it's trying to do. So when I choose a large number over here, it will try to choose a combination of x's and u's where u's are small here and rather large x's over here so that you get this. Of course, you might say, well, I'll choose both of them small. Yes, of course, it's trying to do that. It's trying to choose the minimum. But u and x are not independent. They are connected through this. So you cannot choose u and x independently. They are connected. Okay? So choosing different u's will give you different x's. So the optimization problem will choose the u's, which can be large, that will minimize x. Or it can do the opposite. Choose small u's, which might give you large x's. If you find a solution for where u is small and x is small, well, that's the best solution, of course. Okay, where u and x is small. All right? But here's the goal. We as controls engineers, we can choose f and g and can tell the problem which one is more important to us. Remember, x is the state, u is the control. Okay? So which one of those do you want to put importance on? What is more important? Moving u is the input to the system. U is the aileron, the elevator, the throttle, right? That's u. And x is the state. Angular velocities, angles, velocities, and all that. Which one is more important for you so that it doesn't move too much? Is u important? Should the elevator not move too much? If that's your goal, then you make this one large. Then u will not move too much. But if the elevator doesn't move too much, the aircraft might be moving too much, which means now x will move, the states. You might say, well, I don't want the x moving too much, the states. The u, I don't care. The elevator can do this. Okay? In that case, you might want to have this problem, where you put a large number over here and the x's move little, but u doesn't move too much. Can move a lot, I'm sorry, and x's don't move a lot. So you are going to make that choice. Okay? We call this f and g weight matrices. You are giving weight to one or the other. Either you want the controls to move a lot and x's will be constrained, or you can say the x's are free and I want the controls not to move too much. If you think about it from a controls point of view, from a controller point of view, if the control system doesn't give too much input to the ailerons and elevators, then the aircraft is free to move. Okay? But if you give a lot of authority to the controls, which means the controls are moving too much, basically the autopilot is working a lot, then you can actually make a very unstable aircraft very stable. But the controls are moving too much. Okay? So you give the choice. A good example is this one here. This is an unstable thing, right? This is like an inverted pendulum. If I work very hard, I can stabilize this. So if I work very hard. If I'm lazy, it will fall down. So which one is it? Am I going to work hard and stabilize this? So x's are small, states are small, they're around 0. Or am I going to work little and I'm lazy and x's will be large and eventually become unstable? So which one is it? The best solution is that I don't work hard and x's are small. That's the best solution, of course. But that's not always possible. Does that make sense? Question?
I answered my question.
Okay. Do you understand the philosophy? Do you understand where it is coming from? You're trying to minimize j still. Small number, large number. So, oftentimes you might say, well, I want u and x to be comparable. Okay, I mean both are important. I don't want x to move too much and I don't want u to move too much. Well, then you can just make it comparable. Then choose a j that looks one like this. 0, infinity. I don't know, 10x squared plus 10g squared u squared dt. Now, both of them are 10. They are equal. So a movement in x will affect the minimization problem just like the 10 over here. So, well, if they're comparable, why not make them 1, 1? And for the optimization problem, it doesn't matter. It's trying to find the minimum j. You can make 1000, 1000. It will still try to find the combination of x and u that will minimize j. And in terms of the optimization problem, it doesn't matter. You can have 1, 1. 10, 10, 1000, 1000, Doesn't matter. It will still find the combination of x and u that will minimize j. So although in total the j will be larger if you choose 1000, 1000, the combination that will minimize j will be the same. The combination of x and u will be the same as if you would choose 1, 1. So what I'm trying to say is that if you choose 1, 1, and this is j, and let's say this is x, you would get something like that, and this is your minimum. And this will correspond to a certain pair of x and u. Okay? If you make this 1000, 1000, then j will look like that, and it will still correspond to the same pair x and u, although the j will be larger. And the optimization problem will not change if you multiply this with 1000 or 1 million or 0.1 together. Understand that? What's important is the ratio of f and g. How you compare f and g. Because at the end you're trying to minimize j. Do you understand that? And this is the most important point to understand this whole thing. Because from now on you're not going to do any of these things. You're just going to choose f and g's. Okay? And a lot of people will probably understand that if you choose a large f, x will move little, and if you choose g large, u will move little. But you have to understand why. It is because of this optimization thing. Does that make sense? Yes or no? You can ask me questions if you're not sure.
These f and g functions, they will be matrices, right?
They will be matrices, yes. So I'll show you how to choose matrices in a second. Right now it's scalar, but f and g are fixed constant matrices that we need to choose. But you understand the scalar part, right? Okay. Let's look at the matrix situation. Okay? Let's give an example. I'm not going to solve it, but just to set up the problem. Let's say we have an aircraft with states u, q, and theta. Okay? And control, let's say I have a one-dimensional control, and control is the elevator. And u is x body velocity, and it's in, I don't know, feet per second. Let's make it meter per second, so we are in SI units. Q is pitch rate. Let's make it degree per second, or make it more obvious, let's make it radians per second. And phi, that's the pitch angle, the Euler pitch angle. And let's say this is in radians. And del E is pilot control. And that's again in radians. So pilot controls means this. And this angle here or maybe not do it that way. Let's call this the elevator. Okay, elevator angle. So it is the elevator at the back. So you can move it up and down, and it's the elevator angle, and this is in radians. Okay? So let's set up the LQR problem. So J, it's going to look like this: 1 over 2, 0, infinity. X transpose U, Q, theta. That's the F matrix times U, Q, theta plus E, G, del E. So that is your problem. And you are going to choose now F and G. F will be a 3 by 3, right? So let's do it like that. 1, 2, 3, 1, 2, 3, 1, 2, 3. And G, this will be a scalar. This will be just one number. This one here is F. And this one here is J. So how do I choose F and G? How many numbers am I going to choose? 9. I'm going to choose 10 numbers. 10 numbers. Okay? Numbers to choose for your optimization problem. Okay. So we are going to design a controller where the states are U, theta, V. And this is of course constrained by this. I mean, this is like U dot, Q dot, theta dot is equal to A matrix A times U, Q, theta plus B del E, right? I mean, this is x dot equals ax plus bu. X dot is equal to ax plus bu. X dot is equal to ax plus bu. Okay, this is that. Okay? So these are the states, this is the control, and this is my LQR problem. If I can choose F and G, all I'm going to do is I'm going to write this one, solve the algebraic Riccati equation, find the feedback gain K, and this is what I would call my LQR gain. And what we are trying to do is still optimal control, because there's an optimization problem that we are solving in the back. Okay? So, how do I choose F and G? Here is how I would do it, typically. Okay? First of all, you understand that, you know, if you look at this problem, we had x squared times 1000. Remember? Okay. So, in order to have a good grip on this, this is what I would do. I would just choose 0, 0, 0 here. We don't have to, but let me make the problem a little obvious. I would choose 0, 0, 0 over here. So I would choose only numbers in the diagonal here. Why? Because here's what's going to happen. Multiplying this with this, it will give me u times this, right? Let's call this maybe f1, f2, f3. Let me do it here. U, q, theta, f1, 0, 0, 0, f2, 0, 0, 0, f3, okay, times u, q, theta. So what do I get? I get u, q, theta times f1u, f2q, f3 theta, and here I will get f1u square plus f2q square and f3 theta square. f1 u square, f2 q square, f3 theta square. So this is very similar to this now. So this part would give me f1 u square, f2 q square, and f3 theta square. And this one will be, I will choose one number over here, let's call this g. And this one will be g delta e square, if I choose it like that. So the problem will simply be now like that. J is equal to 1 over 2 theta will be that f1 u square plus f2 q square plus f3 theta square plus g times del e square dt. This is what the problem looks like now. If I set zeros everywhere else except the diagonal, then the problem will reduce to this. And now you can choose f1, f2, f3, and g. And now you actually have the freedom to say u is more important than q, theta is more important than del e. Now you have a weighing not only between the u and the x, you actually can weigh now the states between them by choosing these numbers. You understand that? Zeros, zeros, and you have the diagonal, and that will turn into this. And if you write this and this is now your optimization problem. So just like the argument over here, here you had only 2 numbers, now you have 4. So just like this argument, I'm going to ask you, which one is more important to you? Del E, Q, or U? Which one do you want to move the least? Which one do you want to move the least? I'm just making this up. You might want to say, I want to move the least Q. I don't want Q to move too much. Okay? Make this number large. And you might say, U, the velocity, I don't care, so make it small. You might say the control movement, I want the control movement to be as little as possible. I don't want the control to move too much. The control should move very little. So then make this a very large number, and del E will not move too much. Okay? At the end, the optimization problem will add everything, and it will minimize J. Understood? So it is a very similar concept as this one. As long as I put zeros over here. You don't have to, but you can. Okay? You just choose this. Now this is my optimization problem. Do you understand this part? Okay. But here's the trick. Here's one more trick. There are lots of tricks, but that's good. Because if there are not tricks, then anybody can do it, and nobody is going to pay you to do this when you go and find a job. You have to be happy when there are tricks everywhere. Okay? Because otherwise, it's very simple. Anyone can do this. Who's going to pay you if you just do that? Right? Good. So, one more trick. The optimization problem, this is just a dull optimization problem. It just looks at numbers. It's a computer. It doesn't understand what is what. It just adds these things and tries to find the combination of these controls and the states to minimize J. That's all it does. Now, here's the trick. U is meter per second. So U will always be large. We are talking 100 meter per second, 50 meter per second, right? Large number. Q is radian per second. So it will be 0.1, 0.2, 0.05, very small numbers. And this is del E. It's also small, it's radians. So here's my thing, here's what I'm trying to say. Even if you put 1, 1, 1, 1 to all this U will always be more important because it's a large number. The optimization problem will try to reduce U because any movement in U, let's say from 50 meter per second, you go to 53 meter per second, it's already 3 meter per second, so it's a large number here. Here, a large Q would be 0.5 radians per second. That's already quite large, right? And then you would multiply it with a small number. Even if you put 1, 1, 1, 1 over here, you will become more important. So because this is a dull optimization problem, even if you want to make everybody equal, you first have to adjust these F's and these G's based on the units. So I would start by putting 100 over here, and 1, 100, 100, or maybe 50, or maybe 10, whatever you like, to first put them on the same level. Because any change in U, because it's meter per second, will be a large change. Any change in Q will be a small change, although it is large in terms of radians. So the optimization problem, of course, doesn't understand that. It will be a dull numeric calculation. So the first thing you need to do is put everybody into the same level, meaning that first put F1 small and these ones large, since these are radian and this is meter per second. And after you put everyone onto the same level, approximately, then you can go ahead and say, let's make Q more important, then you slowly increase Q, or slowly increase the control, or slowly increase U. But first put everyone onto the same level in terms of the units, because this is a dull optimization problem.
You said the effect of U is significant, but we are linearized around an equilibrium point, so U is actually the perturbation. How can we say this?
Yeah, but the perturbation of U, when you linearize it, you will see that the corresponding, in the A matrix here, the corresponding derivative here will be a larger number, right? Because a small change in Q will make a large change in U. Let's put it that way, right? A small change in Q will be a large change in U. So any change over here will make a large difference in U. And large means 1 meter per second might not be very large in terms of in real life. But for the optimization problem, 1 is already very large because the rest is radians. Remember that U, Q, theta, and del E, they are still constrained through this equation. They are not independent. Okay? Yes, they are all perturbations around the equilibrium point, but the perturbation in U will be large because it will be meter per second. And the A matrix will be accordingly.
Is it reasonable to compare a non-dimensional number with a one?
If you non-dimensionalize everything, then it will be 1, 1, 1, 1. Then it will be the same.
I'm talking about the U because it's meter per second and the degrees are in radians.
Yes. Well, it is in the problem, and A and B matrices will be accordingly. It is, we are not really comparing. I mean, yes, here we are comparing, but in the problem there will be meter per second and radians and all that. Now you have two choices. You can non-dimensionalize U as well. Then you can compare everyone on the same level. Or you keep them the way they are, but you adjust the F and G's so that they are comparable. In fact, what you're doing here is you're actually, again, sort of non-dimensionalizing. In fact, the way you calculate F1, F2, F3, there are lots of people have tried to find methods. What they do is first divide this by the maximum number of U so that it is some sort of non-dimensionalized, and then add this. You know, you can do lots of tricks here. But this non-dimensionalizing this and adjusting F1 is probably the same thing anyway. Okay? Does it make sense? So choosing F and G is not necessarily the easiest thing. Okay? I mean, it must be, there must be something, and it cannot be too easy. But this requires, choosing this and this, requires a little bit of exercise and experience. Okay? And that's the difference between a good controls engineer and not so good controls engineer. Someone who's experienced and not so experienced. Okay? So you need to get some feeling. Another thing is, of course, you need to understand the physics. If you don't understand the physics, you cannot make the right choices over here. What is more important? Why do I not want this to move a lot more? Well, first of all, U is slow, right? The changing the velocity of an aircraft is not very fast. Changing Q can be quite fast. So what is more important to the problem? Well, I don't want the Q to change much. If I can make this one happen, if I know that Q is not changing too much, then I know U will not change too much, as long as the throttle is constant. I mean, how will U change the forward velocity of the airplane? If you put nose down, theta is large, Q is large, so you do this, then U will change. If you don't change these two too much, then this will not change anyway. So I would put a lot of emphasis on Q, not even on theta, because theta is also kind of changing slow. But Q, the rate, can change a lot. So I would put a lot of weight on Q, less weight on theta and U, and del E, I would probably make it comparable with Q. So that would be an intelligent way an aerospace engineer would handle this problem. Okay? Saying that U and theta will only change if Q is changing. Therefore, the most important one is Q. Don't put much emphasis on these two. And make them somewhat comparable. And then I would look at the outcome. If U is moving too much, I would probably increase this one a little bit, reduce this one a little bit, and then Q and this del E will move somewhat little, and this one move comparable, and then have a good controller. And then I would go back and say, okay, where did I move the closed loop eigenvalues? Right? That's another question. I don't know where the eigenvalues will go. Where will the eigenvalues go? Well, this is K. The eigenvalues will still go to A minus BK. This is still the closed loop system matrix, except K is now this. So where are the closed loop eigenvalues? Well, you can check. A minus B times K will give you the closed loop eigenvalues. Okay? We don't know where the eigenvalues move. That's not my concern in this problem. We do an optimization who's moving a lot. You understand when I say who's moving a lot, right? X in terms of time, I'm talking about this, is moving a lot compared to this, where this is 0, the equilibrium point. This is moving little, this is moving a lot. Same thing with U as a function of time. The control, the elevator is moving a lot, where the elevator is moving little. The best thing is to achieve both. Okay? And this is just stabilization. This is just stabilization because we are still doing this. X dot is equal to AX plus BU. X times K. Boom. You're just stabilizing still. There's no control over here. If you add this guy, this loop will try to stabilize the system, and this guy is trying to give the control to overcome that stabilization. All right? So they will be fighting. This one and this one will be fighting. This will try to bring it back to equilibrium. This one is trying to remove it from equilibrium. You are moving. So if you find the right balance, you will have a stable aircraft where you can still control it. But this loop over here is exactly trying to do this, try to minimize this thing, where you don't move the controls too much and X as little as possible, and you have that optimization. You understand? Any questions? So again, let's give a short break. I will try to do an example in the next hour.